Section 4.2 is introducing implicit differentiation, which is another way of taking derivatives of a function, and we're going to do this in functions where we can't solve it for y. So before we've always had equations where y equals everything in terms of x. These will be ones where it's not that easy to do that. So we're going to treat y as a differentiable function of x, which means that its derivative is going to be dy dx. We're going to take a derivative of both sides of the equation and then solve it for dy dx. What this means here for number 3, our problem is not finished until you have dy dx equals everything else. Now dy dx, we have to use this notation for this. It's going to be a function in terms of x and y together. It's not just in terms of x anymore. This is useful now because we can find relationships of things that are not functions. For example, this right here is not a function, but it could be broken down into smaller parts where we think about it as the blue part, the black part, the red part, and thinking about the derivative individually. But we're going to be able to find that derivative all at once using this process of implicit differentiation, kind of breaking it up into different parts. But rather than breaking up in different parts, if our derivative still has points x, y in it, we might be able to differentiate, well, the derivative at this point versus the derivative at this point, because it'll have y in our derivative, and we'll plug the point in instead. So when we take the derivative of y, if our function was just y something, then we get dy dx. And then if we took the derivative of x, we get dx dx, but really to simplify, as you can think of it as simplifying to 1, we don't bother writing it. This is basically, we're going to treat x the same way that we have before. We could solve this for y, but we're going to do it implicitly instead. Now I take the derivative of 3y, we do that like we would for x, where we use the power rule. But there's actually the chain rule where we're going to look now, the derivative of y is dy dx. Basically, every time we take a derivative involving y, we're going to write dy dx. On the other side, the derivative of x would just be 1. Now to finish this equation, we're going to write this as dy dx is equal to 1 over 3y squared. In the next one, we couldn't really solve this for y even if we wanted to, so we're going to get 6y using the power rule, but since I just took a derivative of y, we're going to write dy dx there, plus my second part, 2, but the derivative of y again is dy dx. Derivative of 5x is still 5. Now to get dy dx out of this, I need to solve this for dy dx. I'm not finished until I do, so I can factor it out, and then I can divide both sides by whatever I'm factoring out of that. So basically the steps that we were using, we were taking the derivative of both sides with respect to x. We want all the dy dx terms on one side so we can factor it out. We solve for that. Now if I want to find the slope of a circle at a given point, this would be my equation for a circle. And so I can write this as the derivative of x squared is 2x, derivative of y squared would be 2y, but we have to have the dy dx in here. And then the derivative of 25 will give us 0. Now again, we need to solve this for dy dx. So we get a negative 2x over here. And if we divide both sides by 2y, we're going to get a negative x over y. Now notice that our derivative is in terms of both x and y. If I had solved this first for y, I could have written this as y is equal to plus or minus the square root of 25 minus x squared, and I could have taken the derivative of that, except that I have this plus or minus here, which means we would have to break this into a couple of functions when we think about our derivative. But in using implicit differentiation, I can just choose whatever point I'm looking at on this circle, and in this case that would be 3, negative 4, maybe down here somewhere, and from that point I can find my derivative from this. So looking at that, if I want my slope at the point 3, negative 4, then I'm going to plug those points into here. X is 3, y is negative 4, and so my slope at that point is 3/4. In the next example, we want to show that we have a derivative at every point on this graph. So we'll start by taking the derivative, which gives us 2 dy dx. Derivative of x is 2x plus sine of y. Now remember, the derivative of sine is cosine. We keep the inside the same, so we still have that y there. And then we multiply that whole thing by dy dx. Now this time we have dy dx on both sides of the equation, so I'm going to need to move this cosine of y over to the other side. I'm going to go ahead and distribute the dy dx out in that same step. Okay, so move the cosine over there, leaving us with 2x over here. And so our dy dx will be equal to 2x over 2 minus cosine of y. Now going back to our original question there, they said they want to know if it's defined at every point on the graph. So the only thing that could be a problem is if we had a 0 in the denominator. And so do we have any zeros in the denominator? We know that the cosine is always between -1 and 1, so we're never going to get a 0 in the denominator. So this is defined at every point in the graph. Or at least the derivative, it is differentiable at every point on the graph. Okay, if we want to find dy dx for every point on the graph, that means we're looking for an equation here. Notice this one is a product of x and y, so we're going to need to use the product rule to do this. Although there might be other strategies. We might move x over to the other side first, but then 0 would be undefined, so let's keep it like this. And so if we use the product rule, derivative of the first is 1 times y, plus the first times the derivative of the second. Remember here that the derivative is dy dx, and the derivative of 9 is 0. I can move my y to the other side as a negative y and then divide both sides by x. So we see sometimes we're having to use product, quotient, chain rule in these things. Sometimes we might have to use them all together. So here I've got x squared y, that's 2x times y plus the x squared times the derivative of y, which is dy dx. So that was all just for this first one. Now moving on to the next group there, in the sine there, the derivative of sine would be cosine. Keep the inside the same, but then we have to multiply by the derivative of the inside. So the derivative of the top, 1 times the bottom, minus the top times the derivative of the bottom. Remember, derivative of y is dy dx. And then divided by the bottom squared. And then equal to, and the derivative of the 4 there would be 0. And this might be quite a bit of work to simplify that, but mostly what I wanted to show there was how we use the product and quotient rule, chain rule sometimes.